Welcome to Ready to Derive. Up until this point, calculus has been all about utilizing the power of the derivative to unlock important features about functions. Now begins the process of reversing our steps. In the same way that division is the inverse of multiplication and square rooting is the inverse of squaring, the rest of the course will explore the process of integration, the inverse of differentiation. In this video, we begin with a recap of my video entitled An Overview of Calculus, giving us a bird's eye view of this inverse relationship, and then we explore the connection between area under a curve and accumulation. So, without further ado, let's get started. So let's begin by revisiting a scenario from the very first video in the calculus series called An Overview of Calculus. So you leave your house by car to visit family. 4 hours later, you arrive at your destination, a distance of 200 miles away. And the instructions had been to make a sketch of your distance from home over the 4 hours. And when I give this to my students, the most common graph that comes up is this one. Just a straight line connecting 0, 0 and 4, 200. And of course, when we sort of dissect that a little more, students realize, well, whoa, wait a minute, what does this motion look like? It means you shoot out of your driveway at a very fast speed, continue at the same speed until you arrive at your destination, and you just like stop dead. So not a very realistic scenario or example, but then the next thing that comes up with, well, what about taking a break? So here's a situation where you drive out of your driveway, instantly achieve a certain speed, and then at this point here you seem to go from a speed of whatever it is, 50 miles an hour, to 0 in no time whatsoever. So again, not very realistic at these corners. And then eventually we kind of perfect it a little more and show a situation where we start out slow and then we speed up and then eventually slow down at our destination. And the whole first half of calculus has been spent looking at how to sketch, in this case, the corresponding velocity, which is really just the derivative of the graph. So we have been practicing, if you think of this as f, what we're about to do next is sketch f prime. And f prime, of course, here, the derivative of a straight line graph in the first graph would just be a horizontal line, f prime, because your velocity is constant throughout. In the second graph, it looks like maybe you're going pretty fast at first because you're going to stop for a long time. So here your velocity is 0. And then you maybe go as fast for the last part of the trip. Again, not very realistic because of the jumps in your velocity in order to achieve this. And then the last graph is the more realistic one. Your velocity, you seem to start out small, then you speed up. You speed up to, at this point, which we now know is the point of inflection, to kind of a maximum velocity. And then you come and slow down to your final destination. So let's take the first example, the straight line path between where you started and your final destination, which is 4 hours later, and you're 200 miles from home. And we sketched the velocity curve in the slide before. The velocity is 50 miles an hour throughout the journey, and you get that by just realizing that you traveled 200 miles in 4 hours, and that comes out to 50 miles per hour. And if we look at a point on this graph, on the position graph, so this point has coordinates 3, 150. That means that at 3 hours, we know we're 150 miles from home. But what we also discovered, and the whole first of calculus is about this, is that that's not the only information contained in this graph. If you find the slope at the point on the graph, you also obviously get the velocity, which is 50 miles an hour. So at 3 hours, so if we look over at this graph, at 3 hours, we have this information that we are going at 50 miles an hour. Sorry, there we go. So the whole first half of the year in calculus, or the semester, as the case may be, we have been looking at differential calculus, where we start with the graph of f, and by analyzing the slope of the graph of f, we create the graph of f prime. And now the second half is all about going in the reverse direction. And this is known as integral calculus, and it has everything to do with area. Now, does area play into this? Well, yes, from this point here, you know that at 3 hours, you're going 50 miles an hour. But if you also examine the area, so you are going 50 miles an hour for a total of 3 hours. So 50 miles an hour, let's have a look at that. For a total of 3 hours, the hours cancel out as units and we get left with 150 miles, which brings us right back to here. This original graph, at 3 hours, we were at a distance of 150 miles from home. So this is the big picture, the overview of calculus. And from this point onwards, we are going to be following the arrow in this direction, integral calculus, looking at area under curves, and basically reversing the whole process of differentiation. So it's sometimes referred to as anti-differentiation, integral calculus, and it's all about the area. So let's look at a real-world example that shows why calculating the area under curve might be something actually that's quite useful. So here we have a rate of snowfall curve predicted for Ottawa, Ontario, and we know it's a rate curve because it says per hour, which means that the units on the y-axis is inches per hour. So the area under a rate curve, as we saw when we considered the rate velocity. Velocity is a rate of change of distance with time. The area can give us so much information. So what can it give us exactly? Let's look at this. It looked like it was snowing or predicted to snow pretty consistently. This is 12 p.m. right here over the first 6 hours. How consistently? Well, let's see. Looks really level there. Again, this is just predictions, but I'm going to say that's about 0.55. What can we do with that? What would that area give us? Well, so let's just look at 6 a.m. to 12 p.m. If we work out the area, it's a rectangle, and we'll say the height of the rectangle, the units are inches per hour, and the width of the rectangle, it's 6 of these hours. The hours cancel, and if you calculated that, that would be 3.3 inches. So what exactly does that mean, 3.3 inches? Is that how much snow had fallen by 12 p.m.? Well, let's look at the corresponding amount of snowfall curve. So this is the amount of snowfall. How do we know? Because it says totals. Let me just put that in red as opposed to per hour. And if we look at, here's 12 p.m. If we look at 12 p.m., it's clearly not 3.3 inches. Well, it shouldn't be surprising, as it looks like there was already some snow that fallen to the ground. So we weren't starting from 0, we were starting from maybe 0.75. So this 3.3 inches represents the amount of accumulation of snow over that time period. In the same way, if we look at 12 p.m. to 6 p.m., another 6 hours, if this looks like it falls right at 0.4, which is perfect. So if we do that calculation from 12 p.m. to 6 p.m., and this time it's going to be approximately 0.4 inches per hour, once again, times 6 hours, the units cancel, and that comes out to about 2.4 inches. So where do we see 2.4 inches? Well, that's from, that looks like to 6 p.m. Sorry, my horizontal line is not the best. So this looks like 2.4 inches, a further 2.4 inches was predicted to accumulate in the next 6 hours. And then if you look over at this curve, you know, after 6 p.m. it looks like there was hardly any snowfall, and that's why over here the amount of snowfall doesn't change. So in total, so the total snowfall over that interval is 3.3 plus 2.4, which is 5.7 inches. So what we learned from taking the area under the rate curve, rate of snowfall from 6 a.m. to 6 p.m., is that the amount of snow that was predicted to accumulate would be 5.7 inches. And that's a very practical application of this concept. So now we're going to practice looking at some different types of rate curves and trying to understand and interpret what the area under the curves represent. So here we have a rate curve of a runner's velocity, and it's decreasing. So at time 0, they're going at 20 feet per second, and they gradually slow down. 10 seconds later, they are going 15 feet per second. So let's start by finding the area shaded in red. So we see that this is a trapezoid. And this, recall, is the area of a trapezoid. And B1 and B2 are the parallel sides. So this must be B1, or could be B1, this could be B2. And H is going to be the distance between the parallel bases. So that would be a half times 20 is the first, is B1, and 15 is B2. And then the distance between those bases is 10. And that comes out to be 175. And then we would like to interpret this area and also give the units. So 175, what's exactly? Well, let's see. 20 and 15 are both y coordinates. So the units of those are feet, or the answer to that would be feet per second. And 10 is along the x-axis, and that's in seconds. So it seems like the unit remaining is feet. So what does this area mean? And with those units, it means the runner traveled a distance of 175 feet over the time interval from 0 to 10 seconds. So let's look at another rate curve. A space shuttle is accelerating at 2 g's. 2 g's would be twice the acceleration due to gravity, so I'm rounding that to approximately 20 meters per second squared. So here we go, constant acceleration over that time period, 8 seconds. So the question, as always, is find the area shaded in orange, and this is a rectangle, so it would be just 20 times 8, which is 160. And again, we are going to interpret this area and give the units. So let's backtrack a moment and think about now the units on the y-axis. So you have to be careful here because this is now meters per second squared. And along the x-axis, it's just seconds. So we can see here that one of the seconds cancels, but you're still left with meters per second as the units. So what does that mean exactly? Pause the video for a moment to try and work that out, as I will reveal the answer now. So this means that the net change in velocity of the space shuttle was 160 meters per second over that time interval. So that's why the units are so important when considering areas under rate curves. So that means that the velocity of the space shuttle increased by 160 meters per second over whatever it was at time t equals 0. So in this third practice problem, we're going to consider an object that's been launched vertically into the air with the velocity curve as shown here. And we notice that this is the first rate curve that actually extends in below the x-axis or the t-axis. So we have some velocities that are negative. So what exactly is going on here? Well, for a moment, let's think of the velocity curve as, let's call it f prime. It really is a derivative. Velocity is the derivative of the height of the object or its position. And we notice that here at 6 seconds, the velocity is 0. And prior to that, the velocity is positive, and after 6 seconds, it's negative. So therefore, we must have a local max in the original function, or the height of the object. So at x equals, or t equals 6, we have a local max there. So what that means is prior to 6, the object is rising, and then after 6 seconds, it's descending. That's going to influence our area calculation. So let's start by finding the area in blue first. So that will be a triangle, half base times height. I think I'll start with the 60 multiplied by 6, and that comes out to 180. 180 what exactly? Well, the units on the y-axis are meters per second. On the x-axis is seconds.
these cancel, leaving us with meters. And what exactly does 180 meters represent? That represents that the altitude that is gained by this object. So in the first 6 seconds, it gains an altitude of 180 meters above wherever it was thrown from. And now let's look at the area shaded in green. Well, it's also a triangle, and it appears to be a half 40 times 4, which would be 80, and of course the units will be the same, meters. But the fact is that we know that the object is actually descending at this point. So if we pay sort of closer attention to what's going on here, we see that the velocity, when we plug in 40, it has a sign. Technically, the velocity is negative 40. So even though area is positive, we will assign, or we need to assign anything below the x-axis as negative velocity, so that our area becomes negative 80 meters. Now, what does that mean? Now, negative makes sense because that means the object is coming back down, so that is the altitude lost. And that matters because if we then want to think about what's the combined area between the velocity curve and the t-axis, well, the object went up 180 meters and then down 80 meters. So if we want to kind of think about it in the long run, what we have going on is that at t equals 10 seconds, the object is 100 meters above the height from which it was launched at t equals 0 seconds. So while it is correct to say that the object traveled 180 meters up vertically and then back down 80 meters, what the area under the curve, taking into account the positive and what we assign to be the negative regions, is kind of the net change in height, and that is 100 meters. So in this last practice problem, we're going to change things up quite a bit. So instead of having time along the x-axis, we are going to have distance in feet along the x-axis. So this graph here is supposed to represent the slope of a trail, as a function of the horizontal distance in feet from the start of the trail. So this is the slope. This is not the actual path you're following. This is the slope of the trail. If you think of this, again, sometimes it's just helpful to think, if you think of this as f prime, then you can sort of think, well, you know, f prime here is 0, changes from positive to negative, so on the original function there must be a local max, right, on f. Here f prime changes from negative to positive, so we have a local min. And here we're not sure if it's a local max or min, but we do know the slope is 0, so we're at the top of, you know, some sort of peak. So what the trail is actually doing, assuming that you're, you know, starting from obviously from the beginning of the trail is actually doing something like that. So notice that in this region here, where f prime is below the x-axis, that's when you're actually going downhill. And everywhere else, you're going uphill. So keep that in mind, but now let's just think about the units. So first of all, this is the area under the curve. We do not have geometric techniques for finding the area under the curve. This being calculus, we will learn that shortly. We'll learn how to actually work it out exactly as well. But for now, let's pretend that area was 20. And let's say, and it's in green because it's above the x-axis, and let's say that's 60. And let's assign this, because we are going downhill here, to be in this region. Let's make that negative 30. If we added those all together, 20 minus 30 plus 60, we would get 50. But 50 what? What are the units in this problem? Well, we know that slope could be inches over inches or miles over miles, or, well, in this case, since the x-axis is in feet, why don't we make it feet over feet? Now, what type of feet? Well, this is This is feet, change in y feet. So let's put feet y, and this is change in x feet. So if we think about the units, the unit of the y-axis is feet in the y direction over feet in the x direction. Sorry, I'm just making up this new notation. And along the x-axis, of course, it's just change in feet in the x direction. So these cancel, and we're left with 50 feet in the y direction. What does that mean exactly? That the change in elevation of the trail over the first 1,000 feet is 50 feet. So assuming, of course, since we will start here because we're starting at the beginning of the trail, that means that even though you did a lot of things in between, this net change in your altitude, or the height of the trail, the elevation of the trail, is 50 feet over that 1,000 feet interval. So in this last slide, we'll just review the important features of an area under a rate curve. So here's a generic rate curve, and we like the area under this curve from A to B along the x-axis. And more often than not, we know that time is along the x-axis, but as in the last example, it could be feet in horizontal direction. So, for one last, for good measure, one last example, imagine this, the y-axis, the rate we are looking at is the dollars of profit per widget produced in a manufacturing setting. And I don't know what a widget is exactly, but I love the word, so I love saying it. So let's just use widgets. And therefore, the area under that curve, that shaded area, would measure the accumulation or net change of a quantity over the interval AB. And what quantity exactly? Well, we know it's always going to be, if you think of rate as delta y over delta x, it's always going to be whatever the numerator is, the delta y unit, which is dollars in profit. And why is that the case? Well, because we know that the units of area will be the product of the units of the x and y axis, because area is basically just length times width. So that would be, if you multiply this whole thing by number of widgets, the widgets cancel out, and we're left with dollars of profit. And one last fact that we're sort of touching on that's going to become very important later, it's called the fundamental theorem of calculus. It's that if you know the amount of the quantity that you have at A, so imagine if you knew the dollars of profit when you produce A widgets, and then if you add the area between A and B under that curve, that means the amount that you've accumulated, then you will actually be able to predict the dollars that you will make in profit by producing B widgets. So it's a little preview of the fundamental theorem of calculus and really the significance of being able to find the area under a rate curve. And that brings us to the end of this lesson. I hope you found it helpful. And if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.